estimates and not just your state error, you would have kind of anticipated it going unstable because you would have seen they weren't converging. You would have seen that they just getting bigger and bigger. So it looked like worked really, what was something that would work well in a computer simulation all of a sudden is actually an unstable controller in real life. So we definitely have to account for this real life effect of these little disturbances. And notice this happens no matter how small Dmax is. Even if the disturbances in real life are tiny, it doesn't matter, it's still unstable. So the tiniest disturbance will make the system go unstable. So there's a few different ways to fix this. We have to use robust parameter updates. One of them would be dead zone. P hat dot equals either beta gamma transpose x if x is greater than Dmax over k, 0 otherwise. We have projection. You have P I hat dot equals 0 if Pi is less than P min and beta gamma transpose x is less than or equal to 0. In other words, if it's too small and it's even growing smaller, if Pi is greater than P max and beta gamma transpose x is greater than or equal to 0. In other words, it's too big and it's even getting bigger. So where P min and P max are known bounds on the parameter. So this system might work pretty well for the robot example we did where the unknown parameters were friction coefficients. So for a friction coefficient, P min would just be 0. You know, friction can't be less than 0. And P max, you could probably pretty easily guess or determine a maximum friction coefficient for a robot. That wouldn't be too much of a problem. So this system, this method might work really well for the robot example we just did. Okay. Third way would be leakage. P hat dot equals beta gamma transpose x minus mu P hat. So this is like what we call a leakage term. Mu is a positive constant. So you can see basically this is basically a term that's trying to drive P hat to 0. I mean, you have hopefully linear systems are starting to come back to you. But if I remove this term and I just have P hat dot equal negative mu P, hopefully everybody can see that that's an exponentially stable linear system by now, hopefully. Otherwise this course really won't make much sense if you can't see that by now. Right? P hat dot equals negative mu p hat would be an exponential stable system that would drive p hat to 0. So this term here is, the effect of it is basically it's trying to drive p hat to 0. And then this term here is essentially trying to drive p hat to infinity. So the idea is they kind of cancel out. And then leakage, the fourth one, sorry, is E modification, which is really similar. So you get p hat dot equals beta gamma transpose x minus nu times the norm of x times p hat. So it's almost identical, except that this leakage term here is multiplied by the absolute value of x. So I'm just going to analyze the stability of a couple of these. I think I'll just do dead zone and E modification because they're probably the most practical ones and the ones that are used probably 90% of the time. E modification is usually used instead of leakage because you get better performance from E modification. Although leakage might be a bit better in terms of stability for preventing p hat from growing big. But in general, people usually use E modification unless it doesn't work. And then they would go to leakage. But they would always try this one first, just because the performance is better. And dead zone is a little bit more practical than projection because of the knowledge. In dead zone, you need knowledge of that D max, the maximum disturbance bound. In projection, you need knowledge of P min and P max. In real life, it's usually a little bit more realistic that you have knowledge of D max. Usually these ones are a little more difficult to establish. So dead zone is kind of a bit more practical, used more often than projection. So those are the ones I'm going to analyze now, but if you want to use one of the other ones in your project, I can definitely show you how to show stability. Dead zone, you need to know D max such that D of x and t is less than D max for all x and some d. And you have B dot equals x, D of x and t minus kx plus p tilde gamma transpose x minus p hat dot over beta. And we're taking p hat dot equals beta gamma transpose x. If x is greater than d max over k. It's 0 otherwise. So let's just draw this out on the board so we can see how we get stability from this. So let's just say we started at this initial condition, x naught, p tilde naught. So that's kind of the initial condition here. So we're in a region right here where b dot is less than 0. So we can't increase in the Lyapunov surface. We can't go uphill in the Lyapunov surfaces. The Lyapunov surfaces are all elliptical. We know that already from the form of our Lyapunov equation that we picked. We picked 1/2 x squared plus 1 over beta p tilde transpose p tilde, so that's basically an ellipse in this space. So we're going to have to follow we kind of have to go downhill here, like that. And then once we're in here, we're flat, right? Because there's no p hat dot once we get in that region. So it just flattens out. So there's no way that I could increase in V if I drew a Lyapunov surface that had my initial condition on it. So I'll just draw it like this. So this Lyapunov surface is a uniform ultimate bound. And if I was going to write it out, I would write B of x and P tilde is equal to V x naught P tilde naught. Okay, so that's an equation of an ellipse, and that's a uniform ultimate bound.
Sorry.
Yeah.
So assume that the initial point is out of that and the opponent surface. It start going to left, and after that it cross the line, it will go into flat.
That doesn't make any sense. This is the initial condition. You can't say, what if the initial condition is outside the initial condition? So this is the initial condition here.
So now, it's not possible to initial condition be a little bit upper?
Well, this is, I mean, you're asking me to put the initial condition somewhere different than the initial condition, which I'm reluctant to do, because that's the initial condition. So that's the initial condition. So this is a Lyapunov surface that's associated with that initial condition. So if I was to move the initial condition up here, I'd just draw a different Lyapunov surface, right? Okay, so does that make sense? So we get uniformly ultimately bounded signals if we use dead zone. Now the best case scenario is if the initial condition is actually in here, but then the dead zone would be, the uniform ultimate bound would be associated with this point here, not the initial condition, because it could grow out to here, right? So there would be some Lyapunov surface there that would be the uniform ultimate bound. In other words, I can't drive the uniform ultimate bound down to 0. There's no way. Yeah?
In modification, you will in kind of trade-off to give a value to the nu, right? Now here, if I change the value of the Dmax, is it any risk of that to have unstable system bursting?
Yeah, exactly. Yeah. So if you pick Dmax too small, then your system goes unstable. So you definitely have to. So Dmax has to be picked according to this, and if this is violated, so if your disturbance goes above the value of Dmax that you're using, then the system could go unstable. Not guaranteed to go unstable, but could definitely go unstable. So it's kind of a pain because, you know, if your maximum disturbance is really quite large in real life that you might expect, then you would have to pick a really big Dmax, and then you'd have terrible performance, right? So it's not. It's only useful when Dmax is likely to be a very small number. It's kind of a useful thing, but if Dmax is likely to be quite large, then yeah, it's not going to be very useful. So let's look at E-modification. So E-modification is, I think, has some advantages over dead zone. So this is the one I would normally use. I don't know. Some people swear by dead zone. I mean, there are books out there on adaptive control that just say, "Good old dead zone. Nothing beats dead zone," and they'll use dead zone through the whole book and never present anything else. But for me, I don't really like this idea of having to pick a large Dmax, and that might wreck my performance. So E-modification seems a lot more attractive for the applications that I look at. So we'll just call it E-mod for short here. So P hat dot equals beta gamma transpose x minus nu x hat. So V dot is equal to x d minus k x squared plus mu x p tilde transpose p minus mu x p tilde transpose p tilde. So V dot is less than or equal to minus kx plus mu p tilde p minus mu p tilde squared. So this one, just keep in mind, I skipped one step here. I was just saying that this was mu x p tilde transpose p hat, right? That's really what I had in my V dot. So I'm just kind of expanding that out. So I just kind of skipped one line of algebra there. So V dot is less than or equal to x d max minus k x minus mu. So all I have to do here is complete the square. It's funny, my daughter's doing like grade 11 algebra right now, and she's like having to complete the square. I'm like saying, don't worry about it. I've never had a graduate student who complete the square, so it's obviously a hard thing. So V dot is less than 0. And my grad students always send me the paper to work on, and I'm always the one that's completing the square in the mathematical derivation section of the paper. Maybe I didn't do that for Rachel, I'm sorry. Did I insult you? I can't remember if I have to do that for you or not. You probably did it.
I think I already had the full derivation.
Oh. Okay. Didn't want to insult you there. So delta x here is d max over k plus mu norm of p over 4k, and delta p so norm of p over 2 plus square root of d max over nu plus p over 4. So note that delta x is proportional to 1 over k. So I can reduce size of delta x arbitrarily. Using my control gain. So the bigger my control gain, the smaller delta x is. So it's a pretty good result that I can. It's kind of like equivalent to linear control, where in linear control you just increase the control gains if you have problems. So it's kind of similar here. If I have like a problem in performance, I can probably just increase the control gain now and probably get pretty good results. So it makes it more analogous to kind of the way I would fix linear control systems. So that's kind of one of the big things that makes E-modification attractive compared to dead zone. Because with dead zone, you're kind of stuck with the dead zone. You can't really do much about it. Well, you can decrease the, well, no, I shouldn't say that, because you can decrease the size of the dead zone with K. But still. This one, you have to increase the K quite a bit to get good results with dead zoning. And this one, you don't have to do as much in terms of increasing K to get your good results. So if I was to draw the uniform ultimate bound, it wouldn't be delta x and delta p. It's a little bit bigger than that. So if I was to draw this out, so the Lyapunov surface is a uniform ultimate bound. So that's V of x and P tilde being equal to V of delta x delta P is my uniform ultimate bound in this case.
So Chris,
Yeah.
if we have a limitation for the value of the K, maybe in multiplication doesn't work for our function, right? Because we need a big K in this case to have a small delta x and delta p.
Yeah, so usually the way this works is that in real life, actually, when you look at the performance of the system, you tend to really stay inside here. So like going out here is quite an unusual occurrence. It's kind of not likely to happen. So a bit of this is due to kind of what happens in reality too, versus just what the math says. So the math says that the worst case scenario is I could go out to here. So that might actually be a fairly large error. So the mathematics in terms of being uniformly ultimately bounded, this might not be so great. Like I might not want to, like this, in terms of performance, this might not even really be acceptable. But it's really just telling me there's a bound on it. But what I find out when I do this in real life is I find out that when the system's well behaved, actually I end up staying inside this region. So really in terms of performance, delta x actually is more like a nominal measure of performance, what I expect to see in the system. And this would be only like a worst case scenario if something really nasty hit the system that was completely unexpected, basically. So I could basically rely on delta x as my measure of performance. So in this I can squeeze down as close as I want to 0 using that value of k. Okay? Yeah?
Aren't you still restricted though on delta P by whatever you have to assume for a delta max? Like if you need your delta max might be assumed to be large for the system instead of
What's delta max? What do you mean?
or D max, I'm sorry. D max.
Yeah.
Just like I know that was the limitation on dead zones. If you have to assume for a large disturbance.
Yeah, in this case, like D max affects, D max really still affects this here, which like I said is the very worst case scenario if something really nasty hits your system. So D max definitely does affect the worst case scenario. But like I said, this delta x here, that can be squeezed in just by increasing k. So then D max doesn't really have a big effect on this in the sense that you can squeeze it down by increasing k kind of as much as you want. But like, yeah, you're right. Like in a worst case scenario, when the worst thing hits your system, this might not do any better than dead zone, or might do worse than dead zone.
Dead zone is assuming the worst case all the time.
Yeah, exactly. Dead zone is assuming the worst case all the time. That's right. And this one's more kind of for nominal performance when you're not getting the worst possible disturbance every time. This would probably definitely outperform dead zone. Yeah, that's right. So dead zone is basically a very conservative design procedure. This is saying, yeah, I might get a huge nasty disturbance sometimes, but it'll still be bounded. But most of the time, I'll be in this kind of nice region of good performance. So let's take a 10-minute break. Well, yeah, let's come back at 3:10, I guess. 3:10? 12-minute break. Come back at 3:10 and we'll finish off the lecture.